So to look at more example, we're going to consider inverse transformation. We know what is a transformation. We have rotation, projection, reflection, and all sorts of transformation. And if the transformation is linear transformation always identical to a matrix times a vector. So all linear transformation is represented by a matrix. We learned this last time. In order to talk about the inverse, let's recall inverse function. When you're going to have an inverse function from x to y, well, in calculus you learned it needs to pass the horizontal test. The function needs to be 1 to 1, right? So only when the function is 1 to 1, you can map it backward. If this is f, this is g, and f map x to y, and g map y to x, basically g undo what the f did. So g is called the inverse of f. Why is the 1 to 1 is so important? Let's look at this example. If you have 1 map to A, 2 also map to A. That's not a problem as a function of f. But it will be a problem if you want to map it backward, because when you map A backward to x, you do not know which one to go, 1 or 2. Then you won't get a function. That's what you learned in all the algebra, calculus, trigonometry. So if we want to extend this idea of inverse to multidimensional vector variable, same idea. The only difference is your map could be from m-dimensional to another m-dimensional if x equals x1, x2, xm. Typically, m equal 2 for plane geometry, m equal 3 for spatial geometry. So we also need that the function be 1 to 1. We call it transformation now. And let the g undo what the f did. So idea is the same. Now back to linear transformation. When you have the linearity, we know any f can represent as a x. That's for Rn, Nd to Nd. Then my A is going to be n by n matrix. And if the B is another transformation from Rn to Rn, and then I write this transformation as By. The B is a n by n matrix. So both of them are square matrix. If you can show me that A multiply B and B multiply A both equal the identity. You remember what is identity? It's this 1, 1 on the diagonal, 0, 0 everywhere. That's identity. And then we're going to call the matrix B as the inverse of matrix A, and also the corresponding transformation G is the inverse transformation of F. Well, when I say transformation, you can look at from geometric point of view, like a rotation, reflection. If I say matrix, you can think about the algebraic expression in this case. Well, let's look at examples. The easiest example is rotation in 2D. In last lesson, we learned to rotate a vector x to an angle theta counterclockwise. This is called the rotation matrix. All you need is multiply the vector you have to this matrix. For example, if theta equal pi over 3, then this is 1/2. That's negative square root of 3 over 2. 1/2 square root of 3 over 2 when theta equal pi over 3. And this is going to be square root of 3 over 2 and 1/2. You multiply this, you get the rotation. So how do you undo this rotation? In other words, how do you get the inverse transformation? Of course, you don't need math. You say just rotate it back. Just rotate it this way. So what means rotate it back? You rotate clockwise, or say rotate a negative theta. So rotate the negative theta, you replace theta by negative theta, and then realize cosine is even, the same, sine is odd, then this will be positive, this become negative, and then your inverse matrix have only one slight difference. The negative move from this corner to this corner. Well, if you want to check, multiply these two matrices, what you're going to have? You should get, by definition, a identity matrix. See? Let me check a few things. Cosine, cosine. You multiply this, cosine square plus sine square, which is 1. And multiply this to here, cosine, sine, negative sine, cosine, cancel out 0. You get back to the identical. So if you look at the transformation, your x back to x. If you look at the a times b, this is a, this is b, you get the identical matrix 1. So a and b are inverse each other. That's one example. And let's look at another example. The inverse reflection matrix. What is a reflection matrix? We talked about this example before. This is the 9y equal negative x. And if I have a vector here, the mirror reflector will be this one. X will reflect to this. How do you undo this mirror reflection? Well, all you need is reflect it back. Do the same thing. So what it means do the same thing? You multiply the same matrix. This is the reflection matrix. You multiply to itself. Basically, you are bouncing back from the mirror twice. You back to the original position. And that's identical. Think you can figure out that in geometry.